Welcome to today's chemistry lecture. In this lecture, we are going to study the concept soluble and insoluble salts. Plus, we will solve our constructed response question from the exercise because almost all the concepts that's included in the questions will be closed up today. So, without wasting any time, let's start our today's lecture. Soluble and insoluble salts. Introduction to solubility factors. When a salt dissolves in water depends on its chemical nature and the condition of the solution. Two primary factors that affect the solubility of a salt are the nature of the salt, means the specific ions making up the compound, and the temperature of the water. General solubility rules. To determine whether a specific salt is soluble or insoluble, we look at the specific group of ions present in them. First, always soluble. The no exceptions group means some ions never form precipitates in school level chemistry. Any salt containing the following completely soluble: all sodium salts, all potassium salts, all ammonium salts, all metallic nitrate, means these are always soluble and make no precipitate in the solution. Mostly soluble means with key exceptions. For example, colorides, bromide and iodides. Most halides are soluble. Exceptions are chloride and halides of silver and lead are insoluble. Let's if we see the sulfates, most sulfates are soluble except sulfate of barium, lead and calcium are insoluble. After mostly soluble, solvent, now we will see mostly insoluble with key exception. First is carbonates. Most carbonates do not dissolve in water except carbonates of sodium, potassium and ammonium are soluble. And next is hydroxides. Most metallic hydroxides are insoluble. Exceptions are hydroxides of sodium, potassium and ammonium are soluble. In a special case, calcium hydroxide is partially soluble. As we can see in the table 18.1, where the solubility of salts in water is briefly described in the table form, where the groups of salts and in the front are soluble table or insoluble table. Salts column shows the group of salts and the solubility or insolubility shows in front of this column says which one is all soluble or non-soluble, mostly or comparatively other are insoluble. It's a very brief table to understand the concepts of salt, their soluble or their solubility in the water completely. Now let's move on our constructed response question from the exercise. So the first question is, why are melting point of ionic salts generally very high? So in the previous lecture we already studied the melting point of salt, where we studied that the ionic salts are composed of a rigid three-dimensional network of oppositely charged ions, cation and anion. These ions are bound together by exceptionally strong electrostatic force of attraction within a crystal lattice. The key factor is to melt an ionic compound, you must supply a tremendous amount of thermal energy to overcome and break down these powerful structure extraction so that the ions can move freely. Because of this massive energy requirement, their melting point are generally very high. The second question is, why ionic salts exist in a solid state? As the same we already studied in the previous lecture, under ordinary conditions of temperature and pressure, the attractive electrostatic forces between the positive and negative ions are strong enough to completely lock the particles into fixed repeating position. key factor is because the thermal energy at room temperature is nowhere near enough to disrupt this tight ordered arrangement. The ions cannot slide past one another flow independently. This results in a rigid, stable three-dimensional pattern, a crystal lattice, which causes ionic compounds to naturally exist as crystalline solid. Third question is, how will you prepare calcium sulfate in the laboratory? So let's see. According to the solubility rules, calcium sulfate is an insoluble salt. Insoluble salts are prepared in laboratory using a process called ionic precipitation or double displacement reaction by mixing two suitable fully soluble salt solutions together. Let's see the procedure. Take a soluble calcium salt solution such as calcium chloride or calcium nitrate. Take a soluble sulfate salt solution such as sodium sulfate. Mix the two solutions. A white precipitation of insoluble calcium sulfate will form immediately. Filter the mixture to collect the solid calcium sulfate precipitate on the filter paper. Wash the residue with distilled water to remove any remaining traces of soluble byproduct. Dry the pure salt between the sheet of filter paper. It's easy to get a insoluble salt at laboratory level by mixing their two soluble solution with each other. The fourth question is, compare the melting point of sodium chloride and magnesium chloride. The melting point of magnesium is significantly higher than that of sodium chloride. Reason: ionic charge. In sodium chloride, the ion carry a plus and a minus charge. The magnesium ion carries plus 2 charge. Lattice acceptance. The higher the positive charge magnitude on the magnesium ion combines its smaller ionic size compared to the sodium exerts a far more intense electrostatic attraction on the surrounding chloride ions. Conclusion is that because the crystal lattice forces in magnesium chlorides are drastically stronger than those in sodium chloride, it demands a much greater input of thermal energy to break apart, yielding a higher melting point. The last question is, how would you prepare pure crystal of copper sulfate in the laboratory? So, copper sulfate is a soluble salt. It is prepared by reacting an insoluble metal oxide or carbonate with the soluble dilute acid followed by crystallization. Let's see the procedure. Measure a fixed volume of dilute sulfuric acid into a beaker and warm it gently. Add copper oxide powder a little at a time while stirring continuously until no more dissolved. The excess unreacted powder settles at the bottom, ensuring all the acid is completely neutralized. Filter the hot mixture, the excess unreacted copper oxide, the clear blue filtrate collected is a copper sulfate solution. Transfer the filtrate to an evaporating dish and heat it gently to evaporate the water until the crystallization point is reached. Leave the saturated solution to cool down slowly at room temperature. As it cools, large pure blue crystal of hydrated copper sulfate will deposit. Filter the crystal out, rinse them quickly with solid cold distilled water and dry them gently using filter paper. As in this procedure, we can get the pure crystal of copper sulfate in the laboratory. I hope you understand this lecture very well. And as for the constructive response question, listen up carefully. You will understand every concept and each point clear.